Hi guys, it's Alana Tucky. I'm back to help with 10.3 number 3 this time. All right, so we're going to test whether mu is equal to 40 versus mu is less than 40. Oops, I'm going to click view an example. It'll be similar, but it won't be quite the same. There's all sorts of parts to this problem. All right, so let's see. We're going to test whether the mean is equal to 50, mean is less than 50, and a random sample of n equals 21 is obtained from a population that is known to be normally distributed. Well, that's convenient. Since the sample size is so small, it helps that we know that it's normal. Complete parts A through D below. So if x bar is equal to 47.5 and s is equal to 11, compute the test statistic. Okay, so let's pull up some StatCrunch, shall we? Because boy, is it easier. All right, so let's see. All I need is stat, and I'm doing t statistics here because this is for the mean. One sample, and I've got summary. They don't have data is when you have like a whole column of stuff, and we don't have that on this problem. So our sample mean was 47.5. Our sample standard deviation was 11, and our sample size was 21. Next. All right, now our null hypothesis is 50. So I'm going to click 50, and we're testing a less than. That's that second one. Next. Calculate. Beautiful. Okay, so that's part of what we need. Hold on, let me copy and paste that into Excel just for my own use. There, hold on, let me copy and I'm going to paste. I'm just going to kind of zoom in. Okay, so just on a side note, I know that this is asking for some other information from us and we're going to have to do a different method, but you can already spot from here, at least you should be able to spot, that we are going to not reject the null hypothesis, right? That's a p-value that is huge. I mean, we only reject the null if you have a low probability, and that is not the case here, right? Any p-value that high, I mean, unless your alpha is 0.20, you're going to be not rejecting. Okay, so just on a side note, so we already know where that's headed, but let's see if we can show it the other way as well, because I'm kind of cheating. I'm sort of using the p-value method a little bit here, and they, I think, want us to use the classical method, but that's okay. Okay, so I think they asked for, let me bring this back up. They want the test statistic. Well, I've got it calculated right here. It's that guy, right? You can also calculate it by hand. It's not hard. You just take your sample mean, which was 47.5, take away your null hypothesis, which is 50, and you divide it by your standard error, which is s over the square root of n. So that's like 11 divided by the square root of 21. Oops, I got to put parentheses around that though, otherwise it won't work right. So 11 divided by the square root of 21. Boom. See? Same thing. So if you didn't have the output or whatever, you could still find it with a basic calculator. Not even hard to do. Oopsie. Don't do that though. All right. So they found it for us, but there it is again. So this is our test statistic. So that's the first part they wanted. Test stat. Oops, it's not statistics. It's not plural. All right. So let me put that under letter A, I think is what they wanted. So that's A, first thing they were asking about. And then what do they want? Yep, see, that's the formula I just used. See that? 47.5, take away 50. Just if you are going to do it with a calculator or by hand or whatever, just make sure you put parentheses around that denominator. So I've got an extra set in there. Very helpful. All right, so then if the researcher decides to test this at the alpha equals 0.05 level significance, determine the critical value. Haha. So we are doing this with the classical method. Either technology or a t-distribution table can be used. All right, I'll do both. So let me just, actually, hold on, let me pull up a picture with Minitab. This is going to take me a second. Hold on. Actually, let me see if I can do it with StatCrunch. You guys aren't familiar with Minitab, so let me see if I can do this. Graphics, no, stat. There it is, calculators. I want a T calculator. Okay, here's where the fun begins. So because my alpha is 0.05 and I'm doing a less than test, see that? Okay, so I'm going to type in degrees of freedom, which is n minus 1, that's 20. I want a less than, right? And I want it to be 0.025. Haha, right? Okay, so what I'm doing is I'm saying, okay, look, degrees of freedom is 20. I want the area in that little tail over there to be, oh, now not 0.0225. I'm sorry. That was my fault. 0.05. Because it's a left-tailed test. Sorry. I was doing two-tailed. All right, so a left-tailed test is going to have it be so that this little red area that I just did is worth 0.05, 5%. Okay. If it was a right-tailed test, you would switch this to that and do 0.05, and then it'd be a right-tailed test. And if it's a two-tailed test, like the one I originally thought of, you can do left or right, it doesn't matter, but you would do 0.025 because you would cut it in half. Because it's a two-tailed test, you have to cut the 0.05 alpha into two pieces, equal pieces. All right, but this is a left-tailed test, so I'm actually going to do 0.05 and press enter or click compute. And it's telling me that that score is negative 1.7. Right. All right, let me take a snapshot of this. This is 10.3.3 video. Okay, let me get to StatCrunch here. I'm going to open StatCrunch again. All right, then I'm going to go to my results, I think is where it is. Aha, 10.3.3 video. I click on it, and I'm going to copy and paste it into my Excel spreadsheet just because I want to be able to refer back to it. And you can get StatCrunch to save stuff, but it's kind of a pain. So there we go. All right, so that's part B. So part B, I can see that the critical value, and this is because it's a left-tailed test, it's got to be negative. It's negative 1 point, well, it doesn't have to be negative, but most often it is. 1747182. There we go. There's part B. Now there are a couple other ways you could find this. So let me give you some hints. So you could do T dot inverse and say 0.05 comma 20. There we go. That's Excel finding it. And then from the table, which of course you're going to have on your exams, let me go back to the problem. There it is. So if I click here on the table, you can say, okay, 0.05, there's the area in the tail. And then I want to drop down to 20 degrees of freedom, and there it is, right? 1.725. Maybe, hopefully. Yep, 1.725. It's just rounded, right? So if you round these to 3 decimal places, you'll get the same thing. So from the table, you'll get, and of course you have to know, that's the one thing about the tables. The table's all positive values because basically they're doing everything like a right-tailed test. That's why it says area in the right tail up above. So if you're on your exam, on your final or whatever, you kind of go, okay, 0.05, 1.725. Okay, so it's negative because it's a left-tailed test, right? This table is only for right-tailed tests, and then you just make everything negative for a left-tailed test. That's all there is to it. That's why they can get away with just doing one table. And the table, of course, is given to you on every exam and the final. Okay, so that's by hand or with computer. Now what do they want? Let me close this. Let's see, so we found that lovely distribution, and we structured our hypotheses. It's a left-tailed test, right? So they gave it to you right in the instructions. So it's a left-tailed test. So we got negative 1.725, all that good stuff. Then you would draw a distribution, but luckily for me, I already used StatCrunch, and it already drew that distribution. That's the beautiful thing about copying and pasting. It's right here, right? That picture. So C is the graph, right? Lovely. And you would kind of label, like that's 0.05 above here for the area, and that value where it's hitting is at negative 1.725. You draw a hand by hand graph, excuse me. And then they want to know, what about your rejection, not rejection? Well, we already knew we were not going to reject because the p-value. I mean, p-value is a lot easier. But if you want to think of it in terms of the classical method, which is what they're trying to get at here, what they're saying is like, look, that red region starts at negative 1.75. So we reject when our sample data is in that red region. It's called the critical region, or the sometimes the rejection region. Different books call it different things. So you reject when you're so far away from what you expect, when you're, in this case, past 1.7 standard deviations. So if we can get past 1.7 standard deviations, we would reject, right? So if we can get farther away than, well, actually, let me put it this way. If the if it's a test statistic, so if the test stat is less than negative 1.725, then reject the null. Okay, but we're not less than negative 1.725. I mean, we are only at negative 1.04, which is right here in the white region. So you're totally not going to reject. Put it another way. Look, we expected 50% or 50 for the mean, right? That's what it was. So we expect 50 for the mean. We got 47.5. Okay, well, that's a little bit lower, but is it like significantly lower? Well, it depends on how much spread there was in this data. And the answer is not really, not for this data set. Our little guy of 47.5 here is only 1.04 standard deviations from the mean. Well, that's not rare, right? I mean, we want to reject when we get rare stuff, being like a couple standard deviations. As a matter of fact, that's what this is. This critical value, what you're finding is how far away do I have to get to be considered rare? How far away from the mean do I have to be considered unusual, so I reject the null hypothesis? And the answer in this case is more than 1.7 standard deviations away. And we're not more than 1.7 standard deviations away. We're less. We're over here, really close to 0. We're only at 1 standard deviation away. Of course, it's a lot easier to think of it with the p-value, because p-value is saying the probability. What were the chances that we got this 47.5 or less? 15.5%. Super high. Well, that's no good. We're not going to reject the null for that. We reject the null when something rare happens. Having something have a 15% chance happening is not rare. We are not going to reject the null hypothesis. All right, I hope that makes it all clearer for you, and I'll see you back here for more videos. Oh, let's double check. I think we did everything for that problem. Yep, we did it all. All right, see you back here next time.